Here's the solution to our simple harmonic motion problems. So the first question we have, we're given a graph representing simple harmonic motion. We're asked what the equation that describes the motion, and we're also asked to mark some times on the graph where the oscillator is in equilibrium and when the oscillator has zero velocity. So I'm going to do the second part first. So let's just indicate where we have zero velocity. We have zero velocity whenever the oscillator changes direction at that particular moment, and that's when the slope of the tangent lines to our graph is zero. That's when it has zero velocity. So this obviously happens up here, over here, over here, over here, over here, and well, imagine this just keeps going over here. So these blue circles represent zero velocity, and we'll make red circles for when it's in equilibrium. So equilibrium is when the position is at its rest position. If it wasn't moving, where would this thing be? And well, that's right here. Here. It's whenever the graph intersects the horizontal axis. So our red circles are equilibrium. Okay, so let's work with the equation now of that describes the motion. So for simple harmonic motion, well, we're dealing with x, not y. So x is equal to a times cosine omega t. Great. So here a is the amplitude, and omega is the angular frequency. I spelt that wrong. Let's just go back. Okay, so recall that omega is related to the period of the oscillator, which is just 2 pi over the, well, so omega is 2 pi over the period. Now if we want to figure out the period, we can go to our graph, and what we need is the distance between either two peaks or two troughs. So if we look at this graph, this distance right here, that is one period. So that time it takes to go, that crest to go that distance, that's our period. And if we look down, that's just 20 minus 10, which is 10. So our angular frequency is 2 pi divided by 10. Okay, so you can obviously plug those numbers in your calculator. You get 0.628 radians per second. Okay, what's our amplitude? Well, our amplitude is pretty straightforward too. It's just the height of one of these peaks. So that's our amplitude, and well, we can read that right off the graph. It's about, 2.5 centimeters. So let's take A to be 2.5 centimeters. And now we have all the information we need to write down the equation. So x is a function of t, and it's equal to 2.5 centimeters times cosine of omega, which is 0.628 rads per second times t. Great. Okay, so now we're going to go to the next problem. We have an oscillator. Its motion is described by this equation here. We want to find the maximum velocity. So we're given the position. So what's the maximum velocity? Well, the maximum velocity, remember that v as a function of t is actually equal to minus a times omega sine of omega t. So that's our velocity. And our acceleration is also a function of time, and it's minus a omega squared cosine omega t. So our maximum velocity is the amplitude of our velocity equation, which is a times omega. So we have a times omega. A, in our case, is 0.15, and omega is 1.2 rads per second. So our maximum velocity, while plugging those numbers in your calculator again, is 0.18 meters per second. And our acceleration, our max acceleration, is given by a omega squared. So this is 0.15 times 1.2 squared, and we should get 0.216 meters per second squared.